Imagine watching the night sky and realizing the math has stopped working. 3i Atlas was supposed to glide by, quiet and predictable. Then it flared awake, far from the Sunday brightness pulsed. Speed shifted. The numbers refused to line up. Are we inside a 1 in a billion moment, or just staring at a loud natural oddball? I will show you the data that made astronomers sit up straight and the questions they whisper after midnight. This is a live investigation that could age by the hour. Join in now, like, subscribe, and share so you do not miss what happens next. Here is the paradox in plain language. Most comets behave like clockwork as they fall inward. Ice warms, gas escapes, dust flows, the coma swells, and tiny jets give a gentle push that slightly bends the path. 3i Atlas broke the rhythm. It turned active while it was still roughly 3 astronomical units from the Sun, a neighborhood where most comets sleep. That distance matters because sunlight is weak. Out there, you do not expect a fountain, yet the fountain turned on. Then there is the chemistry. When the James Webb Space Telescope looked in infrared light, the coma seemed to be ruled by carbon dioxide rather than water. Early estimates placed the ratio near 8-1, which is not just quirky, it is one of the most carbon dioxide heavy mixes ever reported for a comet. Water usually dominates. Here, carbon dioxide leads. That turns the simple picture of surface frost boiling away into a deeper question about how and where this object formed. Now, we test the push. When gas jets fire, the object should feel a measurable shove called non-gravitational acceleration. If the outgassing is strong, the shove should be strong. The surprise is a mismatch. Either the measured acceleration is small for the amount of venting we infer, or the venting is being cancelled by geometry and spin so neatly that the net push is muted. Both paths are uncomfortable. If the nucleus is light, the push should be obvious. If the nucleus is massive, we must ask what it is made of. Rock alone may not explain it. Orbit adds another layer of tension. 3i Atlas is on a hyperbolic path unbound to the Sun, and it is moving against the flow of the planets. Its tilt is only about a few degrees from the main plane, which is oddly aligned for a visitor from interstellar space. Coincidence is a fine explanation in astronomy, yet this geometry invites careful watching. Recent and upcoming passes near Mars, then Venus, then later Jupiter, create windows where even tiny tugs on other bodies could seed long stories we only notice years from now. We need a rule set before the story runs away from us. Step 1. Define normal. A comet brightens as it approaches the Sun following a smooth power with distance. Water leads the chemistry for most. Dust polarization trends sit inside a well-mapped family. Non-gravitational acceleration tracks the heating. Place those baselines on one side. On the other side, place what we have seen here: early activity, carbon dioxide dominance, hints of unusual polarization behavior, and the odd push budget. That contrast is where curiosity becomes testable work. The term black swan is tempting. In philosophy and statistics, it means a rare event that lands with force and only looks obvious in hindsight. If we borrow it for space, we must be strict. Rare is not enough. It needs outsized impact, a trace that cannot be undone, or evidence that our models miss something deep. Does 3i Atlas qualify today? Not yet, but it keeps nudging the boundary, and that is exactly why we keep our notebooks open. What would settle nerves quickly is fragment-level detail. A breakup near the Sun would expose structure and change the balance of jets. It could explain the odd push or make it stranger. What would also settle nerves is a clean, evolving light curve after perihelion that obeys the usual rules. If brightness fades as expected, the story leans toward exotic yet natural. If it spikes or staggers, we look closer. Either way, this is not a story about shouting aliens. It is a story about measuring reality while the clock is running. Here is our pact. We will tour the evidence without hand-waving, we will name what we do not know, and we will keep the thrill without losing the plot. You will hear the most exciting claims, and then you will hear the boring checks that keep science honest. If this turns out to be a once-in-a-lifetime visitor that rewrites a page of comet science, you will see that happen in slow motion. If it settles into the catalogue as a loud but natural outlier, you will know why that answer still matters. Take a breath. The night is young, the numbers are weird, and the next measurement could swing the arc. We move from wonder to framework, what normal looks like, and how 3i Atlas keeps stepping over the line. Then, we will decide what to test first, and how to tell signal from story. The investigation starts now. If we are going to call something strange, we first need a clean picture of ordinary. A garden variety comet is a dirty snowball that warms as it dives sunward. Sunlight penetrates the top layer, ice turns straight into gas, and that gas leaks through cracks and vents, dragging dust with it. The dust and gas surround the nucleus as a hazy atmosphere called a coma. Sunlight pushes the dust into a tail that points away from the sunday. None of this is dramatic. It is patient, predictable physics that we can model in our sleep. Those jets of gas act like tiny thrusters. When they switch on, they give the nucleus a small push that adds to gravity's pull. Astronomers call the extra shove non-gravitational acceleration. It is not mystical, it is bookkeeping. If you know how bright the comet is, about how big it is, and how close it sits to the sun, you can estimate how strong the jets should be and how much the path should curve. Run the numbers, match the path, adjust the model, repeat. Brightness behaves in a similarly tidy way. As a comet approaches the sun, activity rises, and the coma brightens following a smooth power with distance. Closer means brighter, and farther means dimmer, with a slope that falls into familiar ranges that decades of comet surveys have mapped. If the slope is steeper than usual, we suspect lots of fresh ice or fragile dust. If the slope is shallow, we suspect a crust or depleted surface. There is room for personality, but the family resemblance is strong. Composition, too, follows a chorus line. In most solar system comets, water vapor leads and carbon dioxide plays second chair. Carbon monoxide and other volatiles show up, but water tells the story. That is why astronomers often treat water as the baseline. When water rises as a comet warms, we nod. When it stays quiet until the inner system, we also nod. That is normal. It matches how and where these objects likely formed. Even the polarization of scattered sunlight tends to obey the house rules. When light bounces off dust grains, it picks up a preferred orientation. The degree and sign of that polarization change with the angle between the sun, the comet, and the observer. For most comets, that curve with angle sits inside a well-known band. The exact shape hints at the size and texture of the dust. Coarse dust behaves one way, fine, fluffy aggregates behave another. The point is simple. Patterns repeat. Spin and seasons add some texture without breaking the mold. A rotating nucleus turns different vents toward the sun at different times, so jets can flicker on schedules of hours. A tumbling body mixes that schedule. A patchy surface creates morning and afternoon effects. Yet even then, the averages over days and weeks usually fall back onto the familiar brightness slopes and trajectory nudges. Local chaos, global order. The orbit story is equally calm. A bound comet loops in an ellipse and returns someday. An unbound interstellar visitor rides a hyperbola and leaves forever. Either way, the path is a story gravity tells, with small edits from jets. We expect the edits. We can solve for them. If you give us the heating, the area of active vents, and a guess at the mass, we can expect how much that extra push should bend the track. Observationally, a normal campaign looks like this. Photometry to track brightness night by night. Spectroscopy to measure which gases dominate and how those ratios change with distance. Polarimetry to read the dust properties from the way light is oriented. Astrometry to pin down the path and see the gentle drift from jetting. If the pieces agree, the model feels right. If the pieces argue, we go back and find the missing parameter. Why bother laying out all these basics? Because once you have the baseline, deviations stop being vibes and start being measurements. Early activity matters only because most comets sleep at that distance. A carbon dioxide, heavy, coma matters only because water usually leads. A weak measured shove matters only because strong outgassing should have left fingerprints on the path. The frame turns raw surprise into testable claims. There is one more quiet rule. Ordinary comets teach us through repetition. They brightened like this last time, so they will brighten like this next time. They shoved their path by this much last time, so they will shove it by this much next time. Interstellar visitors remove that comfort. There is no last time. There is only now. That does not break physics. It just tightens the leashes on our assumptions. So, our baseline lives on the whiteboard. Heating drives sublimation. Sublimation drives brightness. Brightness hints at jet strength. Jets nudge the orbit in ways we can predict. Water usually leads, carbon dioxide usually follows, and dust polarization curves sit in a familiar band. Keep that map in mind. In the next chapter, we will lay the map beside the new data points and see where the lines fail to overlap. That is where the real story begins. Now that normal has a shape, let us step up to the places where the outline tears. The first rip is distance. 3i Atlas turned active around 3 astronomical units from the Sun, a realm where most comets nap under a crust of cold dust. At that reach, sunlight is weak and chemistry is slow. Yet this object opened the valves early. Imagine standing beside a garden hose in winter and watching water pour out anyway. That is what astronomers saw in the numbers. The second rip is chemistry. When infrared eyes measured the coma, carbon dioxide seemed to lead while water lagged behind. The rough ratio landed near 8-1 in favor of carbon dioxide, which is upside down compared with the usual recipe. Water is normally the headline. Here it reads like a footnote. That suggests either unusual birth conditions or storage of carbon dioxide in a way that releases earlier than water at that distance. Either, the way the cannon gets itchy, the third rip is the way light scatters. When sunlight bounces off dust grains, it picks up a preferred orientation. Measure that orientation across viewing angles and you get a polarization curve that tends to sit inside a friendly band for garden variety comets. Early reads on 3i Atlas hint at unusually strong negative polarization, which is a nerdy way of saying the dust is not behaving like the usual fluff. Maybe the grains are larger or more compact. Maybe they have crusty skins or strange mixtures. The point is not the jargon. The point is the curve looks off. One anomaly can be shrugged away as personality. 2 anomalies start a debate. 3 move the conversation toward category. Distance, chemistry, and polarization do not need to agree to be odd. Yet here they hum in chorus. That does not make the object artificial or magical. It does make the baseline feel a size too small. Now fold in the push puzzle. Outgassing at that distance should leave a signature in the path. A tiny shove added to gravity. If the shove is weak while the venting looks strong, we are missing a term. Symmetric jets could cancel each other. A fast spin could distribute thrust so neatly that it adds up to almost nothing. Dust could be leaving slowly, delivering little momentum, or the nucleus could be massive enough that all that outflow barely nudges it. Each explanation is possible. None is comfy. We can test pieces of this. Watch how brightness climbs and falls across days, not just weeks. If the light curve shows regular pulses, that hints at spin and vent geography. If it shows sudden steps, that points to surface failures or pocket vents bursting open. Track the color of the coma. If the carbon dioxide to water balance evolves as it nears and then passes the sun, we learn about layering and heat flow. If it stays carbon dioxide heavy, we learn about formation far from a warm star. Polarization can do heavy lifting as well. Different dust, sizes and textures paint different curves. If the curve keeps landing outside the family band, we can rule in or out certain mixtures without touching the nucleus. Combine that with how the tail behaves in solar wind, and you start to triangulate the dust recipe. These are not glamorous measurements. They are careful and patient, which is where breakthroughs hide. There is a trap we must avoid. Once you see one odd number, it is easy to see every number as a hint of something exotic. That way lies noise worship. The discipline is to ask the same question each time. Does this deviation reduce when we account for viewing angle, for temperature, for instrument quirks? If it survives those boring checks, then it deserves a louder voice in the story. So, here is our working read. Early activity at an unfriendly distance suggests either a surface primed to vent carbon dioxide or a skin that fractures under small temperature changes. A carbon dioxide heavy coma suggests deep cold origins or trapped reservoirs near the surface. Odd polarization suggests dust that is more compact or coated than the cotton candy grains we see in many comets. The push mismatch suggests symmetry or mass. None of these alone rewrites physics. Together they demand attention. We are not yet in the land of grand claims. We are in the craft of stacking modest facts until a shape appears. The first cracks in the model are not a collapse. They are invitations. Next, we will place those cracks on the map of the orbit itself and walk the path 3i Atlas chose through our solar system. Geometry can be a prankster. It can also be a clue. First, we map the path. 3i Atlas is not coming home again. The orbit is hyperbolic, which means unbound. It dips toward the sun, then climbs away forever. That alone is not shocking. What lifts eyebrows is the way it threads the solar system. It moves retrograde, which means it runs against the traffic of the planets, and its tilt from the main. The planetary sheet is only a handful of degrees. For an interstellar traveler, the near alignment with our cosmic highway is uncommon enough to earn a second look. Think about what that geometry means for what we can measure. A low tilt keeps the object in familiar skies for many observatories across Earth, which improves nightly coverage. Retrograde motion boosts relative speeds during planetary flybys, which sharpens any tiny gravitational nudge into something we might detect later in precise astrometry. Hyperbolic escape means the clock is ruthless. Every week, the comet grows fainter and the window narrows. Geometry gives and geometry takes away. The timeline matters. Perihelion slipped past around the end of October. Earlier in the month, the object went by Mars at roughly 0.19 astronomical units, which is about 28 million kilometers. That is close by the yardsticks of planetary dynamics. In early November, it comes within roughly 0.65 astronomical units of Venus. In the first quarter of next year, it cruises inside roughly 0.36 astronomical units of Jupiter. None of these is a danger pass. They are distance markers that help define where small gravity nudges might have been planted. A skeptic will say coincidence. Space is large and angles add up to patterns by chance. The skeptic is not wrong. Yet coincidences become interesting when you can write predictions against them. If a close Mars window mattered even a little, we should see a hair of extra uncertainty bleed into the orbit fits that cross that date. If Venus or Jupiter matter, we should see similar hairlines later. The practical test is boring and beautiful. Measure and refit. Then measure again with better instruments and longer arcs, and ask whether the residuals shrink the way they usually do. There is another side to geometry that does not make headlines, yet absolutely shapes the story. Retrograde motion changes the way jets push. When gas vents fire, on a fast retrograde nucleus, the direction of thrust combines with orbital motion in ways that can mask or magnify the net push in different parts of the path. A near-ecliptic tilt also keeps solar wind interactions and tail orientation within well-mapped regimes, which helps us separate weird dust physics from weird viewing angles. The shape of the path is not just a line, it is a laboratory setup in motion. Now we talk about alignment and the story our brains want to tell. A visitor from between the stars slips into our system almost in the plane and heads the wrong way. It skims the neighborhoods of Mars, then Venus, then Jupiter, as if it knew where to aim. That sentence tastes like intention. The danger is to mistake taste for test. Celestial mechanics can throw near-plane arrivals because interstellar space does not care about our preference for tidy randomness. Sampling bias can make aligned arrivals feel clustered because we are better at finding what passes through our most observed skies, so we ground the drama in checklists. Track the precise sky position night after night, and let the orbit solver tell us where the tiny unmodeled forces remain. Compare inbound and outbound non-gravitational terms once the activity settles into its post-perihelion rhythm. Examine whether the brightness evolution across each planetary window shows the kind of small shifts that could reflect tides or geometry rather than folklore. If those lines come back ordinary, we have a story about a loud visitor that merely walked through crowded rooms. If they do not, we have a trail to follow that does not rely on vibes. The path also sets up fair opportunities to learn about the nucleus itself. The Mars window correlates with spacecraft that watch the upper atmosphere and the magnetotail of that world. The Venus window puts the coma under angles that change how sunlight scatters toward us, which can help polarization studies. The Jupiter window happens when strong solar wind structures often sweep the outer system, which may give us clear tail dynamics against a gusty backdrop. These are not claims of mystery. They are invitations to use alignment like a lever. In short, we resist the romance and embrace the map. Hyperbolic escape means urgency without panic. Retrograde motion means speed without threat. Near-plane inclination means visibility and repeated chances to test. Close approaches mean calibration points for the quiet type of consequences that matter over years rather than days. We will watch the path rather than the narrative about the path. If there is a whisper of intention in the numbers, it will have to pass through the same sober gates that every other claim must pass. The plane is crowded. The plane is also honest. Numbers are supposed to settle our nerves. Here they make our pulse tick faster. Start with the basic promise of comet physics. Heat turns ice to gas. Gas leaves as jets. Jets push. You do not need exotic math to feel that chain. Now put 3i Atlas on the scales. The jets look busy from the brightness and chemistry, yet the recorded shove on the orbit is modest. The force ledger does not balance. Somewhere between the nucleus and our models, a term is hiding. There are honest ways the push can disappear without breaking any laws. Symmetry is the first suspect. Imagine vents, firing in roughly opposite directions. Each jet shoves hard, but the net cancels like two friends tugging a rope with equal strength. Rotate that setup, and the cancellation can hold through a full spin cycle. If that symmetry is real, the path looks gravity clean while the surface is a carnival of activity. Beautiful idea, rare in practice. Spin is the second suspect. A fast rotating nucleus can smear thrust around, so the net over a full turn is small. Think of short impulses that average to almost nothing. The light curve would then show periodic pulses in brightness as vents come into sunlight and slip into night. To find a strong repeating rhythm in those pulses, spin becomes more than a shrug. It becomes a measured property that explains the vanishing push. Dust speed is a third suspect. Momentum transfer depends on how fast mass leaves the surface. If the gas blows but carries dust slowly, the momentum shot into space can be less than expected for a given light output. Slow dust is not the headline in most comets, but dust physics loves mischief. Grain size, cohesion, and the way carbon dioxide drags solids can all tune the speed. Polarization can help here, because grain size and texture leave fingerprints in scattered light. Now we come to mass and density. The stubborn answer to a weak shove is a heavy body. If the nucleus carries more mass than we guessed, the same thrust yields less acceleration. Early size estimates for 3i Atlas span a wide range because they depend on assumptions about surface reflectivity and composition. If the nucleus is toward the large end of that range, if it is packed tighter than the airy rubble piles we often imagine, the small measured push becomes easier to accept. Yet that road raises a stricter question. What mixture makes a small interstellar body that dense and that dark at the same time? We can triangulate. Step 1 is to pin down spin. That comes from high cadence photometry and any repeating brightness modulations that hold across several nights. Step 2 is to watch the posture of the jets indirectly through asymmetries in the coma and tail. If structure repeats with the spin period, symmetry starts to look plausible. If it does not, cancellation loses power. Step 3 is to improve the size estimate with thermal measurements. If we can measure how the surface warms and cools, we can bracket both size and reflectivity rather than guess. The most delicate test sits in the orbit fits themselves. Non-gravitational parameters are usually treated as smooth functions of distance from the sunday. For a messy nucleus, the push can be lumpy. If we solve inbound and outbound legs separately, and the fitted push changes sign, amplitude, or phase in ways that match a measured spin, we are closing the loop from light to force. If the fits refuse to behave even with these freedoms, the missing term is not symmetry or spin. It is something we do not yet know how to describe. There is a seduction we should name. When force budgets refuse to close, the loudest room starts to whisper about exotic materials or intentional control. Resist the shortcut. Before we borrow drama from science fiction, we squeeze every drop from geometry, spin, jet physics, and measurement bias. We ask whether our chosen functional form for the push is too tidy. We test different thermal lags between sunlight and vent response. We swap dust models. We try and fail to make the oddness go away. If it does not go away, we earn the right to say so. That does not mean new physics. It means the current comet cookbook is missing a recipe that interstellar ingredients force us to add. That is still a thrilling outcome. It would change how we interpret brightening slopes, how we plan spacecraft flybys, how we estimate impact probabilities when non-gravitational drifts matter. A better model buys real safety as well as better stories. For now, the verdict is stern patience. We have a lively nucleus, a modest shove, and several plausible ways to hide thrust in plain sight. We have a path to test each of them with light curves, polarization, thermal reads, and careful orbit solving that respects messiness. If a simple fix closes the books, we update the model and move on. If not, the gap itself becomes the discovery. Either way we win, because reality gets sharper and our next visitor finds us ready. You can feel it the moment you walk into a control room or scroll a research thread. The room splits. One side says comet and points to the telltale signs of a natural body under stress. Water is present, dust is flying, light curves rise and fall with solar heating. Nothing here demands anything beyond ice, rock, and sunlight. The other side says look harder. They circle the mismatch between outgassing and measured push, the carbon dioxide heavy coma, the odd polarization. They do not claim science fiction. They claim the model is not closing, and that is exactly when you do not lower your eyes. These are not caricatures. The cautious voices have earned their caution over decades of disentangling messy data that later fell neatly into place. The provocative voices have also earned their edge by noticing the one detail everyone else dismissed. Between them sits the public and the press, trying to turn a long scientific vigil into a headline. The risk is not only being wrong, it is being loud and wrong in a way that wastes attention when attention is the rarest resource in modern astronomy. So what would settle this without theatrics? Evidence that forces both sides to nod. A clean spin period, confirmed by repeating brightness pulses across independent observatories. A thermal size estimate that trims the mass range from wild to narrow. An inbound and outbound comparison of the non-gravitational push that changes in ways consistent with the measured spin and vent geometry. A stable evolution in the carbon dioxide to water balance as the object rounds the sunday. A polarization curve that either slides back into the family band with better angles or keeps defying the catalogue after careful calibration. These are not philosophy. They are tasks. There is also a way to argue without saying a word. Allocation. When the international community quietly puts more eyes on a target and extends the schedule through key windows, that is a vote. Telescope time is the currency of belief. If 3i Atlas keeps earning nights after the news cycle moves on, it means the data still has questions worth asking. If the calendar dries up, it means the numbers settle back toward ordinary, even if the story was dramatic for a week. We should name the asymmetry that drives many decisions. If you ignore a low probability path that later turns real, you miss the chance to catch the first signs in time to learn the most. If you chase every low probability path with full sirens, you starve other science. The antidote is triage done in daylight. Rank scenarios by plausibility and impact. Push the high-impact ones up the queue only if a small set of triggers fire. Keep a public checklist so the world sees the bar, then sees when the bar is met. Caution is not cowardice. It is cadence. You answer the exciting question only after you have tried to kill it. Is the odd acceleration real after you model spin, vent symmetry, and dust speed? Is the carbon dioxide ratio stable after you correct for aperture effects and background subtraction? Does the polarization still look strange after you change phase angle and fix instrument offsets? Cynicism is different. Cynicism assumes the answer before the test. We do not have time for that. There is another divide we rarely say out loud: comfort with uncertainty. Some scientists are allergic to dangling threads and would rather call an outlier early than live with it. Others would rather sit inside the question for months if it means the answer is earned. The story around 3i Atlas will reward the second kind. The object is a fast visitor and a slow puzzle. The only way to keep up is to let the timeline be what it is and to narrate the gaps with honesty instead of noise. What about the public conversation? You play it straight. You say what was measured, what it could mean, and what would change your mind. You avoid the hook that says alien first and the hook that says nothing to see here. You invite people into the process. You show the boring plots and the thrilling ones with the same voice. You let the audience feel the difference between a wild guess and a worked example. That is how you build trust that survives. A plot twist. In the end, rooms that split do not have to stay split. They converge on the strength of shared datasets that refuse to bend to bias. If 3i Atlas is just a noisy snowball from a very cold place, the curves will pull it back into the fold. If it keeps flexing outside the lines after every dull correction, then the fold expands and the textbooks get a new page. Either outcome is a win for anyone who came for truth rather than for a team. We leave this room with a plan. Next up, we define what a black swan should mean in space and set criteria that are hard to pass on purpose. If the object ever crosses those lines, we will know it without shouting. If it does not, we will still have learned why it looked so strange at first glance. Curiosity over certainty, method over mood. That is the only way to keep a split room from becoming a broken one. Black swan is a phrase that tempts headline writers, but it only earns its feathers when the rules are strict. In everyday language, it means a shock we did not see coming, that hits hard and only looks obvious after the dust settles. To make that useful for astronomy, we turn it into questions with measurable teeth. Did the event land outside the range our models honestly allowed? Did it carry consequences that mattered beyond a paper or two? Did it leave changes that cannot be undone? Did it hint at intent or at physics our catalogues do not cover? If the answers trend yes, the bird is real. If they wobble, it is just a noisy goose. Start with unpredictability that outpaces the model. Not a small stretch, not an edge case we could have seen by widening a parameter. We mean a jump that makes the old model fail in a way that cannot be patched with a simple tweak. If a comet's chemistry sits far outside the family but still flows from known sublimation physics, that is surprising, yet absorbable. If the observed forces refuse to match any physically reasonable combination of spin, symmetry, dust, speed, or mass, then we are closer to a model break. The bar is high on purpose. We protect the word rare by starving it of lazy uses. Now weigh impact. A true space black swan is not just curious. It changes the way missions are planned, telescopes are scheduled, or defenses are built. Think of an object that forces an update to planetary protection protocols, or that compels a rework of how non-gravitational drifts are handled in long-term risk projections. If the effect is only that a handful of specialists argue about grain sizes, that is not a black swan. That is Tuesday. Next is irreversibility. Did the event leave a fingerprint that history cannot scrub? An orbital shift seeded today that echoes for decades. A new parameter required in every future orbit solver. A calibration standard retired because it no longer matches reality. Reversible noise does not count. Permanent change does. The last and spikiest test is intent or beyond catalogue physics. We do not demand aliens. We demand signals or behaviours that refuse to fit natural randomness after every boring correction has had its day. A narrow-band pulse that repeats with sky position across independent instruments. A trajectory alteration that cannot be produced by jets no matter how you spin the body or shape the vents. This test has the highest payoff and the highest burden. Extraordinary claims meet a ladder, not a red carpet. With the yardstick set, we place 3i Atlas against it. Unpredictability first. Early activity at roughly 3 astronomical units, an 8-to-1 tilt toward carbon dioxide, and hints of unusual polarization are off the beaten path. They strain the house model but do not shatter it. There are plausible stories that use deep cold origins, surface layering, and dust texture to explain most of it. The force mismatch between outgassing and shove is the sharpest thorn. If inbound and outbound solves continue to disagree after we solve for spin and symmetry, unpredictability inches up the scale. Today, it is provocative, not definitive. Impact next. The object has already redirected attention and telescope time. That is an impact on schedules, not on doctrine. If it forces a rewrite of how we estimate non-gravitational drifts for fast visitors, that begins to count. If it shifts how we handle interstellar survey triage or how we value polarization in quick-look pipelines, that also begins to count. For now, the practical effect is a louder checklist and a tighter watch. Irreversibility looks light. No recorded orbit shifts of other bodies yet. No permanent change to standards proven. If a fragment behaves in a way that compels a new thrust model for vented bodies, that would leave a lasting mark. If not, the wake this object leaves will be cultural rather than mechanical. Intent or beyond catalogue physics remains a clear no for now. No vetted signals, no trajectory behavior that survives the dull explanations. The hydrogen line remains a siren song we will not chase without discipline. The best use of this box is patience, while independent teams reprocess noisy archives near perihelion, and while future visitors offer a repeatable geometry to test. So, the verdict is sharpened curiosity. 3i Atlas does not clear the black swan bar today. It does enough odd things to justify the extra eyes and the stricter math. It does not justify myth-making. The better story is the harder one. We set criteria before the climax, then keep them in view while the plot twists try to knock them from our hands. If the object crosses a line, we will say so, and you will hear the evidence that pushed it over. If it never does, that answer is still a win. It means our models can stretch, absorb, and grow without breaking. That is how science earns trust while the night keeps surprising us. Here is the map of possibilities, not predictions, paths. 8 ways an odd visitor could move from curiosity to consequence. We keep the drama in check by tying each path to a simple test. Pass the test, and the idea climbs a rung. Fail it, and the idea goes quiet. That is how we stay brave without being reckless. Orbital domino is the slow burner. A tiny tug seeded near a planet propagates through the years until a small body drifts into a new neighborhood. The test is relentless astrometry. Fit the orbit of 3i Atlas across the Mars, Venus, and Jupiter windows, then cross-match for subtle residuals in co-orbitals and known minor bodies. The signal we want is a small but consistent drift that survives new data rather than shrinking away when we extend the arc. Fragmentation event is the messy artist. Comets crack, vent, and shed. The weird case is a fragment whose motion refuses to match simple ejection. The test is fast photometry, and immediate orbit solves for any secondary points of light. The signal we want is a new component that decelerates against the expected vent direction, or that holds a path inconsistent with reasonable thrust models after we fold in spin. Solar disruption is the lightning chase. The sun explodes with flares on its own schedule. A comet should not flip that switch. The test is timing that leaves no wiggle room. Check coronagraph movies and flare logs through the perihelion day and the days bracketing it. The signal we want is a major eruption that lands inside the tightest geometry window, aligned in a way that is very hard to dismiss as luck. If the sky stays quiet, this scenario steps down. Artificial signal is the highest mountain. A narrow band ping near the hydrogen line is the temptation. The test is brutal. Multiple instruments, clean radio frequency interference rejection, match sky position, and a repeat, or an unmistakable modulation that common sources cannot fake. The signal we want is coherence that survives reprocessing and independent pipelines. One instrument plus one blip equals folklore, not finding. Atmospheric anomaly is the subtle thread. A charged, tail-brushing a magnetosphere could nudge the ionosphere in ways that delay signals. The test is coordinated monitoring. On Earth, we watch total electron content from global positioning receivers and ground magnetometers. At Mars, we watch auroral proxies and plasma instruments around the date of closest geometry. The signal we want is coincident disturbances that line up with the comet's position in a narrow window and that do not match solar drivers already on record. Disclosure dynamics is about process rather than physics. Big collaborations often release calibrations and memos in waves. The test is pattern literacy. Track formal circulars, workshop announcements, and data re-releases linked to this object, looking for clusters that correspond to private anomaly chasing. The signal we want is a cadence that suggests elevated scrutiny without the breathless claims that would tip into rumor. This path is real even when nothing dramatic is found, because it shows how institutions handle surprise. Psychological cascade is the mirror that looks back at us. Attention can bend choices. The test is to watch behavior, not belief. Telescope time allocations, emergency briefings, policy chatter, even market signals in satellite risk insurance. The signal we want is a measurable shift in resources or decisions that persists after headlines fade. The cure for this path is also the measure for it. Clear public checklists that keep excitement from outrunning evidence. Reality glitch is the strangest door. Timing systems are our rulers and clocks. A cluster of tiny offsets across independent instruments would be alarming. The test is harsh and simple. Gather pulsar timing arrays, spacecraft telemetry, and atomic clock networks around the perihelion window, then smash them together in a blind analysis that looks for the same small residual at the same time. The signal we want is correlation that survives every known propagation and calibration effect, and that vanishes outside the window. A map like this keeps us from drifting. It lets us say yes to curiosity while printing the receipt for every claim. It also gives you a way to follow the hunt. If a fragment appears, you will know which numbers to watch. If a solar flare lands in the wrong hour, you will know which next steps matter. If the sky stays quiet, that quiet is also a result. Quiet can be the best answer in science, because it lets us prune ideas and pour our attention into the ones still standing. Above all, we commit to a rule that has no loopholes. The more extraordinary the path, the colder the blood we bring to the test. That is not a lack of imagination. That is how imagination survives contact with reality. Next, we step into the first two paths that could change real risk over long spans of time: the small nudge and the clean break, the whisper and the crack. Picture a billiards table the size of the solar system. One gentle tap lands today, the ball you care about rolls, for years, and only then does it clip a corner pocket you never saw from the break. That is orbital domino. A tiny change in speed at the right moment compounds into a position error that grows with every loop around the Sunday. The math is dry, the stakes are not. Start with scale. Change the speed of a small asteroid by 1 millimeter per second and walk away. After 1 year, that quiet nudge becomes roughly 30 kilometers of position shift. After 10 years, it is roughly 300 kilometers. If that rock lives near a resonance with a giant planet, gravity can amplify the drift. The point is not panic, the point is sensitivity. Space is stable until it is not, and the line between the two can be thinner than we like. Where does 3I Atlas enter this story? Geometry. The passes near Mars, then Venus, and later Jupiter are not close in any alarming sense, but they are close enough to make dynamicists pull their chairs in. A hyperbolic visitor brings a moving gravity field and a cloud of dust and gas. The direct pull on major planets is trivial. The indirect influence on smaller neighbors and co-orbitals is where whispers can start. You will not see a shove. You watch for a long echo. Detection is all about astrometry with stamina. First, pin down the comet's own track, with enough precision that unmodeled forces on it do not leak into the rest of the fit. Then, bracket windows around each planetary pass and reprocess high-quality positions for small bodies that share those neighborhoods. Mars Trojans, near-Mars crossers, Venus co-orbitals, and main belt asteroids with periods that bring them near the geometry in question. You are not looking for drama. You are looking for residuals that refuse to shrink when you add more data. The inverse square law keeps us honest. Gravity fades quickly with distance. That is why most potential nudges will be lost in noise. But chaotic systems do not ask for large pushes, only timely ones. A millimeter per second, delivered to an asteroid that already sits awkwardly near a resonance, can send it on a different road entirely over a few decades. If the nudge moves a body from a quiet path into a corridor where thermal forces like the Yarkovsky drift push it further, you have the first two tiles of a chain. We can practice on archives. Take well-tracked asteroids that passed near earlier interstellar visitors and test whether their post-encounter solutions improved as expected when new observations arrived. If residuals behave normally then, we earn the right to be skeptical now. If any looks stubborn until a subtle parameter was added, we learn what to test this time. Science gets faster when it remembers its own scars. Modelling must err on the side of boredom. Run many simulations with realistic uncertainties in the comet's mass, its exact path, and the catalogue of small bodies in reach. Flag bodies whose future positions diverge meaningfully across those runs. Then aim telescopes to Titan, the error bars on those specific objects in the coming seasons. If the spread collapses back to ordinary, you close the file. If it stays wide, you keep watching. A good null result is not a failure. It is a cleared room. Communication matters here more than poetry. The public should hear the logic without the alarm. We are not predicting a collision. We are auditing the places where small differences grow. The payoff is long-term safety. The same vigilance that might catch a domino seeded by 3I Atlas will also sharpen our eyes for the countless tiny effects that already shape asteroid risk forecasts. From sunlight pushes to mutual nudges inside rubble piles, there is also a reward for pure curiosity. If the object seeded nothing at all, the act of looking improves the catalogue of near-planet companions and cleans up their orbits. That helps mission designers, sample return planners, and anyone who wants to fly through those neighborhoods without surprise. The discipline we invest today becomes a library. Other missions can borrow tomorrow. So what would count as a meaningful signal? A handful of small bodies whose post-fit positions, after the relevant windows, remain offset in the same direction across independent observatories by an amount that exceeds what observers routinely see when arcs lengthen. A pattern that is geographically and temporally coherent, not a random drift sprinkled across the sky. A nudge with a story you can tell forward and backward in time without hand-waving. The whisper to shove arc is slow. That is fine. Patience is part of the craft. We set the markers now, we revisit them in months, then in years. If nothing grows, The quiet becomes evidence that our models already capture what matters. If something does grow, we will have the timestamps to trace the path and the humility to say the first domino was a visitor that never meant to touch anything at all. Either way, the table gets safer, and our predictions get less polite and more true. Comets break, heat sneaks into cracks, pockets of gas build pressure, rotation stretches weak seams, and a nucleus that once looked solid sheds pieces like a tired glacier. That is ordinary drama in the inner solar system. The question is not whether a breakup can happen, but whether the way it happens tells us something new about 3i Atlas and the missing force in our ledger. Start with the usual script. A normal breakup announces itself as a sudden jump in brightness, followed by a lopsided coma. The main body keeps moving on its predicted line, while one or more faint companions trail behind at small separations. Those sprouts fade as dust spreads and sunlight grinds them down. When you fit their motion, the fragments behave like chips kicked off by pressure and heat. Speeds are modest. Directions make sense. The tail geometry looks messy but explainable. Now the interesting version. Imagine a secondary point of light that refuses to play along. It drifts in a direction that does not match a simple kick, or it seems to decelerate against the direction of outgassing, or its brightness pulses on a rhythm that does not match the parent. None of those behaviors demand fiction. They do demand tighter modeling. Internal caverns can channel gas in odd arcs. Spinning shards can aim thrust in changing directions each time sunlight hits a new face. Cohesive slabs can pivot like sails and ride pressure gradients in ways that look perverse at first glance. How do we catch the difference between messy, natural, and truly off-pattern? With cadence and patience. Night-to-night photometry at steady exposure times lets us spot step changes that signal a crack rather than simple day-to-day heating. High-resolution images from multiple observatories let us separate real secondaries from background stars that only look like companions during a bad seeing night. Point spread function fitting helps decide whether a suspect speck is a fragment or just a knot of dust in the coma. Motion speaks louder than sparkle. Once a candidate fragment is identified, short arcs over several nights can be fit to a simple model that combines a gentle initial push with the same gravity the parent feels. If the fit holds, we log it and move on. If it refuses to hold even after you allow for solar radiation pressure and reasonable outgassing from the child object, then we have something worth the extra telescope time. A small radar ping would be wonderful, though unlikely at these distances. More realistic is a multi-band campaign to see whether the color and polarization of the fragment match the parent or hint at layers newly exposed. Rotation can hide inside the light. If the parent nucleus is spinning fast enough to flirt with structural failure, the light curve often shows it. Repeating peaks and dips tell us when active patches turn into and out of sunlight. If a breakup follows those peaks by a fixed delay, we get a clue that thermal stress, rather than chance, was the trigger. If fragments appear at times that do not line up with the rhythm, the fracture mechanics may be stranger than a simple spin story. Either way, the timing is a microscope. There are false trails everywhere. Star fields near the ecliptic are crowded, and a smeared background star can masquerade as a newborn shard. Thin clouds can skew brightness enough to fake a small surge. Guiding errors can stretch the coma and look like fresh structure. That is why independent confirmations matter. When two teams on different continents report the same bump, the same offset, and the same fade rate, confidence climbs. When only one pipeline sees the excitement, humility is the better move. What would count as weird in a way that matters for the force mismatch? A fragment whose path implies thrust vectors that cancel the parent's push far more neatly than chance would allow. A secondary that appears, brightens, and then holds a trajectory that suggests internal pressure, cycling, as if pockets are venting in a repeating sequence. A breakup event that changes the parent's non-gravitational parameters in a direction that our simplest models did not predict. Any of those would push us to rethink the cookbook for jet physics and momentum sharing. Breakups also seed futures. A faint companion that drifts onto a longer loop could become a distant wanderer that returns in a century with its own personality and risks. Dust clouds from a split can load meteor streams that graze planets years later. None of this is cause for alarm today. It is cause to treat every fracture as a time capsule. Inside is information about strength, layering, and the inventory of buried ices that a smooth coma could never reveal. So we watch, slow and steady. We keep the exposures honest, the cadence regular, and the comparisons fair. If 3i Atlas falls apart in textbook fashion, the pieces will still teach us about its build and help close the books on the missing shove. If it falls apart with the wrong rhythm or in the wrong directions, the crack becomes the clue, and the clue becomes the next experiment. Either way, a breakup is not the end of the story. It is a lens. Time to stare at the biggest character in the story. The sun is a boiling sphere of plasma whose magnetic field knots and snaps on its own schedule. Flares erupt. Coronal mass ejections throw billions of tons of charged particles into space. Power grids flicker on Earth. Auroras bloom far from the poles. Against that backdrop, a comet is a moth in a hurricane. Still, the question hangs in the air because it is irresistible. Could a visitor like 3i Atlas do anything at all to tip an already unstable system? Start with scale and sanity. Gravity first. The sun outweighs a comet by a number so absurd it turns this route into a dead end. There is no gravitational trigger here that matters. Electromagnetism next. The comet carries an ionized coma and a long plasma tail. The solar, wind streams outward and drapes magnetic field lines through everything. Where plasmas meet, currents can flow, and field lines can reconnect. That is real physics, not wishful thinking. The honest question is not if interaction exists, it is whether any interaction could be strong enough and timed tightly enough to light the fuse of a solar event. Now draw the geometry. The solar wind does not blow straight outward like a hose. The sun rotates, so the field spirals like water from a spinning sprinkler. This spiral makes lanes of magnetic connectivity. If the comet's plasma sits on a lane that threads back to an active region on the sun, then charged particles and disturbances could in principle ride that lane. Picture a loose telephone wire humming between the two. It is a fragile picture, but it gives us something testable that is better than hand-waving. The test needs clocks and cameras. We check coronagraph movies that watch the solar corona every few minutes. We check flare, catalogues. We check radio bursts from the sun that often accompany eruptions. Then we draw a narrow window around perihelion and the days just before and after. We look for eruptions aimed roughly along the line that also connects to the comet's sky position through the spiral. We expect noise, because the sun is active in general. We want timing that is uncomfortably neat. An eruption that lands right when and where the weak coupling would be strongest. There is a second filter. We ask whether the eruption was unusual in power or direction, compared with neighbours in the same solar rotation. If the sun was spitting flares every few hours anyway, coincidence becomes cheap. If the sun was quiet and one lunge happens right on the window, eyebrows go up. This is not courtroom proof. It is a way to raise or lower the temperature on the idea without leaning on narrative alone. We can also check downstream effects for consistency. If a coronal mass ejection really launched along the line, bunch of sight during the window, then space weather monitors between the sun and Earth should see it on the timeline the speed predicts. Ground magnetometers should show signatures that match the arrival. If they do not, any apparent match at the sun itself is probably a trick of alignment. The sky loves to rhyme. It rarely tells lies for our benefit. There are caution signs everywhere. Sun-grazer comets have dived through the corona for centuries, while the sun did whatever it wanted. Many passed without a twitch. Some coincided with action because action is common. We remember the overlaps and forget the misses. That is how folklore grows. The antidote is to count misses as carefully as hits, and to publish the count even when it makes the story less glamorous. If the logs around perihelion show nothing special, this path steps down the ladder. That is not a disappointment. It is a useful boundary. A quiet sun during the tightest geometry window tells us that any comet-to-sun coupling is either too weak to matter or too broad in time to be a trigger. We can file that lesson under good housekeeping for the next interstellar visitor that tempts the same question. If the logs show something close and strong, the work is just beginning. We would need to replicate the method on past comets and on random control windows to measure how often chance alignment mimics cause. We would need to ask whether the same apparent coupling repeats across multiple passages with similar geometry, not just once. Only repetition takes a coincidence and turns it into a pattern. Until then, the safest word is maybe, and the smartest move is restraint. So can a comet nudge the Sunday? The sober answer is almost certainly no in a way that matters for policy or power grids. The curious answer is that the plasma universe does not like absolute words. and the geometry gives us a graceful way to test. We will check the clocks, check the movies, and name what we find. If the sky stays quiet, we downgrade the idea and move on. If it murmurs at the exact wrong hour, we listen harder and demand that the murmur repeat under the same conditions. Either way, the sun reminds us to respect scale, and the test reminds us to respect evidence more than thrill. There is a reason the idea of a single perfect ping makes hearts race, a narrow whisper from the dark. One tone that says pay attention, then silence. The storytelling writes itself, the science does not. A one-off signal is the hardest thing to trust. It is also the easiest thing to imagine. That mix is dangerous if you care about truth more than goosebumps. Start with how searches really work. Radioscopes stare, sweep, and record. Pipelines clean the feed by removing obvious junk from Earth and orbit. The tools are good at catching repeating beacons and easy patterns. They are less friendly to short-lived oddities because the first rule in radio astronomy is do not get fooled by us. Human machines make a mess of the sky. Aircraft, satellites, ground transmitters, a farm of sensor gizmos that never existed when the classic playbooks were written. One spike that lasts a breath will be thrown in the trash unless multiple sanity checks line up. Now picture the geometry during the perihelion window. 3i Atlas is near the sun on the sky. Many radio teams avoid pointing close to our star because the background blazes. The ones who brave the glare lean hard on filters that protect the feed from saturating. Those filters can also kill the very transients that would make a headline. This is why the idea of a single perfect ping is a trap. If the instrument was set up to survive the sun, it was also set up to doubt anything brief. If the instrument was set up to catch anything brief, it was probably not watching. What would real look like? Multiple telescopes, separated by a long haul of kilometers, each with different electronics, each seeing the same tone from the same patch of sky at the same instant. A frequency pattern that does not land on known channels used by human hardware. A drift across frequency that matches the relative motion of source and Earth in a way that a local transmitter cannot fake. The tone would either repeat on a schedule you can predict, or arrive with a modulation that carries structure, but a natural burst cannot mimic. Hard to meet, not impossible. This is the bar you clear before the word artificial takes a seat at the table. The hydrogen line is the classic temptation because it is a smart place to talk across the galaxy. It is also crowded with earthly noise and protected services. If you fish there, you cast into a river full of boats. Smarter is a plan that spreads across multiple bands, watches known interference maps, and still keeps an ear on the romantic frequencies as a courtesy, rather than as a crutch. The more ways you can say this is not us, the better your night of sleep before you show the world. Archival data is where the real action is for a Gottes just Krub, fast visitor. There is a chance someone, somewhere, was already watching the right patch of sky for unrelated reasons. Fast radio burst surveys sweep wide, solar watch programs skim near the limb, deep field monitors stare at one place for weeks. The safest path is to reprocess those feeds with algorithms that are curious first and defensive second, then hand any candidates to a separate team whose job is to kill them without mercy. If a candidate survives both moods, you have an adult signal. We can also do better next time. Put a narrow band piggyback mode on a few solar telescopes during perihelion weeks. Ask large radio arrays to set aside a thin slice of time for interstellar visitors that reach a trigger threshold of weirdness in their optical data. Practically, that means carbon dioxide heavy, unusual polarization, or a force budget that will not close after the boring checks. When the optical team waves the flag, the radio team does not roll their eyes. They roll the dish. If the sky coughs just once, what then? You do not announce. You convene. You line up the raw voltages, the pointing logs, the weather notes, the human checklists that say who waved a phone near the control room or switched a heater. You ask a partner continent to repeat the observation at the same sidereal hour. You retune. You rotate the polarization. You watch again. A real sky source will not care about your cables or your pride. It will care about geometry and physics. If a second wink arrives when and where the first says it should, you step onto a higher rung. There is a softer win hidden in the hard rules. Even a clean null result teaches. If teams coordinate around a strange visitor and find nothing, the negative becomes a template. The next time the play runs smoother. The time after that, it runs on muscle memory. The long arc here is not alien first contact. It is a culture of looking well when the window is small. The one ping-only problem is really a patience problem, dressed in romance. It asks whether we love a good story more than we love a careful test. Our answer has to be yes to the test, every time. If there is a voice in the noise, discipline is the only way to hear it twice. Until then, we will keep listening with clear eyes and colder blood, and we will admit that silence is a kind of data too. Space weather is not just an aurora on your phone wallpaper. It is a living electric skin around our planet called the ionosphere, a high-altitude layer where sunlight knocks electrons off atoms and turns air into plasma. Radio waves bend there. Navigation signals slow there. When the sun burps a storm, this layer ripples. The question for 3i Atlas is modest but important. Could a charged tail and a puffed-out coma, guided by solar wind, add a faint extra wrinkle to that already twitchy layer at the right moment and place? First, the geometry test. The comet's ion tail points almost directly away from the sun, like a windsock in a gale. If that tail sweeps past the Earth-Sun line near our orbit, a thin drizzle of extra-charged material could wander into the magnetic funnels that guide particles toward the poles. That is the only path with a chance. No direct collision, no dramatic crossing. Just a brush, and only if the angles cooperate. We would expect an effect that is small, fast, and easy to hide inside normal solar mood swings. So, we design a listening campaign that is humble and specific. On Earth, global positioning receivers already watch the sky for changes in electron content because those changes delay timing signals. Stitching thousands of receivers together gives a world map of the ionosphere every few minutes. Ground magnetometers feel the tiny currents that flow when the upper atmosphere is disturbed. High-frequency radars see flows in the polar sky. Classic ionosondes ping the layer to measure its height and density. None of these instruments care about comets. They care about electrons. That is, good. It means they will be honest. We stack the data by window and by place. Pick the hours when the comet sunline passes nearest Earth's magnetic lanes. Pick a control set of neighboring days with similar solar conditions. We ask a simple question. Did total electron content rise? Did magnetometers twitch? Did radio paths bend more than expected inside the exact window when a brush could happen? And did the pattern land in both hemispheres in the way field lines would predict? If yes, we keep digging. If no, we file a quiet no and move on. The sun is the loud neighbor who makes this hard. Flares and coronal mass ejections pump energy into the same system, and they do it often, especially near solar maximum. To avoid fooling ourselves, we subtract the sun's behavior first. We remove intervals with obvious solar drivers. We compare with a network at similar longitudes, where the comet geometry is unfavorable. We test whether any blip that survives has the right shape for a thin, brief addition of plasma rather than a global surge. The point is not to be clever. The point is to be fair. There is a second laboratory right now that we would be foolish to ignore. Mars. The comet's early October pass came much closer to Mars than to Earth. Mars has no global magnetic shield. It wears patchy, fossil magnetism in its crust, so its auroras appear in scattered arcs when the solar wind couples to those patches. Orbiters can sense how charged particles fill its upper air. If a comet tail brush can matter anywhere, Mars is the good place to catch it. The prediction is crisp. A short, localized glow or a spike in charge density near the time and longitude where the comet geometry points, while the sun's broader influence stays flat. Even if both worlds show nothing, the experiment pays for itself. The same filters and cross-checks will serve the next visitor, and the one after that, until we have a template that runs almost by muscle memory. If, on the other, panned, the numbers nudge upward in that narrow window, we do not declare victory. We ask for repetition. We look for the same fingerprint on future interstellar comets that share the right angles. We demand a pattern that persists across objects and seasons. 1 coincidence is romance. 2 are luck. 3 begin to teach. There is a practical frontier here that excites me. We can add a comet trigger to the daily space weather dashboard. When an interstellar visitor crosses an angle threshold, the system flags the window to the ionosphere networks and the Mars teams. No heroics. Just a quiet note that says watch the next few hours with a sharper eye and archive the raw data at higher fidelity. The cost is small, the potential lesson is large. In the end, this path is not about spectacle. It is about whether a faint extra drizzle of charged dust can leave a measurable fingerprint on delicate systems we depend on, from navigation timing to radio links. If the answer is no, we have drawn a clean boundary that future storytellers should respect. If the answer is yes, even barely yes, we have learned something new about how small travelers converse with big fields in a plasma universe. Either way, we will tell you exactly what the numbers say, without a single violin in the soundtrack. When people imagine discovery, they picture a sudden press conference and a headline that ends arguments. That is not how most truths arrive. In space science, discovery moves like a file being passed hand to hand down a long hallway. Drafts, calibrations, cross-checks. A quiet workshop on a weekday afternoon. A public circular that sounds boring on purpose. If you know how to listen, the rhythm tells a story without anyone raising their voice. Start with the leagues that actually watch the sky. National agencies, university teams, independent observatories. Networks built for planetary defense that schedule campaigns months in advance and then add extra stations when a target starts. Acting interesting. 3i Atlas already earned that kind of attention, not because someone whispered secret, but because the data kept asking questions. Telescope time is a vote. When the calendar stretches, you can feel the vote tally rise without a single dramatic word. The process has a shape. First come the quick alerts that say what was seen and when. They are lean on adjectives and heavy on numbers, which is a feature, not a flaw. Then come reprocessing notes that explain a new flat field, a better background subtraction, a fresher wavelength calibration. After that, a cross-instrument meeting where teams reconcile differences and agree on shared definitions. Finally, a short paper appears that pins down a value range and lists the caveats in small print. From outside, it looks slow. From inside, it feels like discipline. Because the world is noisy, the same shape can be misread. A calibration update right after a rumor looks like a cover-up to someone who wants one. Closed. The workshop about outgassing models sounds like a secret trial. A pause before a public statement is taken as fear. The cure is to narrate the cadence before the tension spikes. Tell people that calibration releases always cluster near campaign peaks. Explain that some meetings must be small if they are going to turn disagreement into progress. Name the difference between saying nothing and saying not yet. There is a reason language feels careful. Scientific claims are not just fact statements. They are invitations to be wrong in public. Teams write with brakes on because every strong noun becomes a commitment, and commitments need receipts. In a story like 3i Atlas, the receipts are light curves, spectra, polarization angles, and orbit fits that other people can reproduce. When those arrive, the verbs get bolder. Until then, the right tone is steady, not shy. You can read institutional pulse through logistics as well as words. When a network issues an extended observing campaign that bridges perihelion and the outbound leg that is raised stakes. When a radar group requests a standby window, even though the odds of a clean echo are poor, that is real curiosity. When a radio facility sets a narrowband piggyback to run during specific nights, that is a team acting on a small chance with big payoff. None of this requires secret knowledge. It requires coherent plans and good faith. Now the hard part. How to handle claims that carry asymmetric risk. Suppose a fragment candidate appears with a motion that is hard to explain. The right first move is not a splash. It is to ask a competing team to kill the finding. Different telescope, different reduction pipeline, different weather. If the result survives that unfriendly hug, you move to the next rung and write a brief public note that says exactly what would upgrade the claim. The same ladder holds for the dream of a narrow-band ping. The bar for a press event is not one instrument and a good plot. It is replication with independent hardware and sky geometry that rules out our own machines. The audience plays a part in this too. Demanding instant certainty is a fast way to get comforting fictions. Rewarding careful doubt creates room for real answers. You can help by learning the telltale signs of honest work. Do the authors publish their data? Do they show the checks that could hurt their conclusion? Do they say what would change their minds? That is what trust looks like in a field that handles more unknowns than certainties. If the next weeks bring nothing dramatic, expect a trail of small releases that sharpen numbers and shrink error bars. That is success. It means the object is sliding back toward ordinary, and the early noise is being tamed. If the next weeks bring something odd that survives the gauntlet, expect the language to change. You will hear words like robust and independent and repeatable. You will see figures that overlay inbound and outbound curves with a clean, stubborn difference. You may even see a schedule for new instruments to take a crack at the same puzzle. Disclosure in space is not a reveal. It is a record. It should feel less like a stage and more like a ledger that anyone can audit. 3i Atlas is moving fast, but the method does not. That is by design. We trade speed for accuracy, so the story we hand to the future is sturdy. If there is a twist in this plot, it will arrive in the same tone as every other real discovery you have ever seen. Calm, documented. Ready for strangers to test. That is how you tell the truth without setting the room on fire. Attention has mass in the human world. It bends schedules, it pulls money, it tilts decisions. When a story like 3i Atlas catches fire, the heat is not just emotional, it becomes operational. Telescopes pivot, review boards reshuffle priorities, and quiet projects lose their slot because the public and the press want answers now. None of that requires malice. It only requires fascination and a deadline. We have seen this movie before. In 1910, newspapers warned that Earth would drift through a comet's tail, and people bought bottled antidotes for imaginary gases. During the year 2000 software scare, governments spent billions to fix clock logic that might have failed. The fixes were mostly the right call. The panic was not. The lesson is slippery. Fear can be wasteful, but preparation can be wise, and untangling the two requires a clear head at the very moment nerves are loudest. Here is how attention turns into motion in space science. First comes a spike in views and headlines, which becomes calls to agencies, which becomes meetings about optics as much as about optics. Someone asks for a white paper that did not exist yesterday. Someone else asks whether there is any near-term risk they would be blamed for missing. That question moves time. It nudges telescope schedules and keeps a target on night logs a little longer than it might have otherwise. What looks like curiosity on YouTube becomes a line item in a scheduling tool. Markets feel it too. Satellite operators read space weather briefings with a little more edge. Insurers revisit a clause about geomagnetic risk and tail events. None of that means the sky is falling. It means stories shape how people weigh small probabilities. Low chance and high consequence is a mix that sponsors care about, and attention changes the way that mix lands on a spreadsheet. There is also a feedback loop inside the lab. The loud claim gets more independent checks because nobody wants to be the last to see a real thing. That is good. It can also create a mirage where normal fluctuations look like patterns simply because more eyes are watching. If you look at enough plots, you will find a zig that lines up with your favorite hour. The antidote is rules agreed upon before the heat rises. Pre-register what will count as evidence and what will not, then live with that list in public. This is not a plea for silence. It is a case for pacing. Excitement is a resource. Spend it on measurements that have leverage. A night of high-cadence photometry across 3 longitudes can lock a spin period that clarifies the force budget. A coordinated polarization sweep can pin down dust sizes that unlock the scattering riddle. Those deliverables cool the room because they replace maybe with something you can point at. Hype fades when numbers clarify. Hype roars when numbers wobble, and people fill the gaps with wishful storytelling. Social media is both a gift and a trap. It lets scientists speak directly, show raw plots, admit uncertainty, and invite people into the process. It also rewards speed and certainty, which are the 2 traits most likely to betray a complex story. The best threads share what changed a mind. They say we thought X on Tuesday and Y on Friday because we corrected Z. That narrative teaches the public what real progress sounds like. It puts drama where drama belongs, in the act of getting less wrong. You play a part in this. When you reward calm updates over loud predictions, you teach the system what to amplify. When you ask what would change your mind instead of, is it aliens, you pull the conversation onto solid ground. When you share a debunk with the same energy you shared the rumor, you become part of the scientific method rather than a pinball in the attention arcade. Curiosity does not mean credulity. Skepticism does not mean cynicism. The balance is a muscle. If 3i Atlas settles into the catalogue as a noisy comet with a cold birth and odd dust, the weeks of elevated attention will have still done real work. We will have tightened models of non-gravitational drift for interstellar visitors, improved polarization playbooks, and rehearsed cross-checks between Earth and Mars networks for atmospheric effects. If it refuses to settle and continues to pluck the strings that models cannot mute, then the same attention will have paid for the follow-through. Either way, attention becomes gravity when it funds patience instead of panic, so we keep the volume high enough to wake the world and low enough to hear the data. We let fascination open doors and let evidence decide which rooms we stay in. The next minutes and hours are not just about what 3i Atlas is, they are about what we become when the sky sends a hard question. Do we chase the loudest narrative, or do we build the most honest one? We can choose, and we will. We live by the illusion that time is tidy. Phones sync to satellites. Spacecraft talk to dishes half a world away. Pulsars sweep the sky with rhythms so steady that sailors from another civilization could steer by them. Then you look closely and discover the truth. Timekeeping is a chorus, not a solo. Every instrument hums with tiny imperfections, and the universe loves to tap those imperfections with a mischievous finger. Start with the clocks. Atomic clocks on Earth. Set the pace for navigation, radio arrays, and deep space tracking. They are astonishing, and they are still physical objects that feel heat, vibration, and human maintenance. Now, add pulsars, the lighthouses of dead stars. Their beams sweep us with a crisp tick. We time those ticks to the microsecond and sometimes better. A pattern that drifts can signal everything from a gust in interplanetary plasma to a wave in the fabric of space-time. This is why astronomers build pulsar timing arrays. They watch dozens of pulsars and look for shared wobbles that betray something big moving through the cosmos. Into that delicate practice walks our visitor. The idea is simple to state and hard to prove. During the perihelion window of 3i Atlas, did multiple instruments record a small cluster of timing offsets that look a bit too coordinated? If yes, is there any world in which the comet or its environment helped nudge the signals we rely on? The sober caveat arrives first. A small icy body cannot slow time. Its mass is trivial. If something shows up, it would be a propagation trick, not a relativity lesson. Charged dust and plasma can delay radio waves. Solar wind can roughen the path. Instruments can hiccup. The game is to separate those boring truths from any tempting story. We design the test to kill the coolest idea first. Step 1 is geometry. If a fingerprint exists, it should cluster in directions that make sense for the comet's sunline, not all over the sky. Pulsars near that line could show tiny arrival time shifts within a tight window. Pulsars far from that line should stay quiet. Step 2 is control windows. We take matching slices of time before and after perihelion, when the sun was in a similar mood, and ask whether the same pattern appears. If it does, the comet is irrelevant. Step 3 is hardware diversity. Offsets that appear at two observatories with different receivers and different time standards are worth another breath. Offsets that live only at one station are probably born there. Now fold in the weather of space. The ionosphere over each station delays radio waves depending on electron density. That density changes with solar activity and even with local time. We remove intervals with obvious solar drama, and we use independent maps of total electron content to subtract routine swings. The interplanetary medium adds another smear. Clouds of charged particles drift between planets and change the arrival time of a pulse by a whisper. Good pipelines already model this. We push those models hard and then ask what residue is left. Spacecraft telemetry gives us a second lens. Probes around Mars and near the outer planets stamp their messages with clock times tied back to Earth. If a weird propagation effect touched multiple communication paths during the same hours, receivers across the network might log small and simultaneous timing nudges. The test is again a blind comparison. Pull the logs for the perihelion window and for nearby quiet windows. Do the statistics without knowing which is which. If the perihelion set pops out only after you peak, you have fooled yourself. There is also the human factor. Firmware updates, a swapped frequency standard, a cable reseated by a careful hand on a cold night. These leave fingerprints. A good lab notebook and honest engineering notes are as important as any sky model. When in doubt, we ask a partner station to repeat the measurement, while ours is deliberately misconfigured in a benign way. If the pattern follows our mistake, the sky is innocent. How small is still meaningful? A handful of microseconds across 2 or 3 instruments is interesting only if the sign, the timing, and the sky positions line up with geometry, and only if control windows refuse to produce the same T's. The bar is high because the prize is fragile. If you lower the bar, you buy a ghost. If you keep it high, you might earn a clue. What happens if nothing shows? That is a good day. A. Clean null sharpens our priors. It tells us that any comet-scale propagation effect sits below the sensitivity of current networks, and we can stop wasting attention on an idea that does not pay rent. What happens if a small, stubborn, well-shaped cluster survives? Then we do not announce a mystery. We build a repeat plan for the next visitor that crosses the same angles. 1 object is a story. 2 begin a pattern. 3 make a case. The myth of perfect time is useful. It lets us navigate and it lets us build instruments that talk to each other across oceans. The practice of imperfect time is better. It forces us to check, to compare, and to doubt with craft. If 3i Atlas leaves no trace on our clocks, our tests still grow stronger. If it leaves a whisper that refuses to fade under every dull correction, we will hear it together and we will earn the right to wonder. Until then, we trust the rhythm and we respect the noise. Time to put stakes in the ground, not vibes, positions. We list what each path would need to advance and what would make it fall back. Then we name the few measurements that carry the most leverage in the coming weeks. If we are wrong, we change the score. The point of a scorecard is not bravado. It is accountability you can watch. Orbital domino sits at medium plausibility and high impact. It moves up if small bodies near the Mars, Venus, or Jupiter windows show post-fit residuals that refuse to shrink as new astrometry arrives. It drops if extended arcs collapse those residuals to ordinary noise. What to watch now is nightly positions for Mars Trojans and near-Mars crossers, plus any minor bodies flagged by simulation as sensitive to those dates. Expect months, not days, before this one clears its throat. Fragmentation event sits at medium plausibility and medium to high impact. It moves up if we see a clean brightness step, followed by a resolved secondary whose motion will not fit a simple kick even after we account for radiation pressure and spin. It drops if surges smooth out into standard heating curves, and if every candidate secondary turns into a background star on better seeing nights. What to watch now is high cadence photometry and multi-band images that separate a dust knot from a true shard. Solar disruption sits at low plausibility and high potential consequence. It moves up only if a strong solar eruption lands inside a very tight perihelion window with geometry that lines up through the spiral of the solar wind back to the comet. It drops if the sun stays ordinary for that window, or if any eruption fails to produce the expected downstream signatures at monitors between sun and Earth. What to watch now is coronagraph movies and space weather timelines that match cause to effect without hand-waving. Artificial signal sits at very low plausibility and extreme impact. It moves up if 2 or more radio facilities with different hardware log the same narrow feature from the same patch of sky, with a Doppler drift that fits the relative motion, and if that feature repeats or carries unmistakable structure that nature does not fake. It drops with any single station blip, any interference hint, or any failure to reappear at the predicted sidereal time. What to watch now is quiet coordination rather than loud claims. Atmospheric anomaly sits at low to medium plausibility and low to medium impact. It moves up if total electron content maps, magnetometers, and high-frequency radars show subtle, coincident signatures that land in both hemispheres during the exact geometry windows, while solar drivers are flat. It drops if those maps are quiet or if patterns mirror ordinary solar wiggles. What to watch now is the Earth network around the window and the Mars plasma data near the early October pass. Disclosure dynamics is not about physics. It sits at medium plausibility and medium impact for trust. It moves up if you see extended observing campaigns, calibration re-releases, and the cross-team workshops that cluster around specific anomalies. It drops if schedules shrink and language cools, in step with numbers that settle. What to watch now is the cadence of circulars and the shape of the shared checklists rather than speculation. Psychological cascade sits at medium plausibility and medium impact. It moves up if attention shifts resources in lasting ways that outlive headlines. It drops if schedules normalize and if policy chatter fades as measurements tighten. What to watch now is telescope allocations, briefings, and how quickly review boards return to baseline priorities. Reality glitch sits at very low plausibility and extreme conceptual impact. It moves up only if multiple clock domains report tiny, consistent timing offsets during the perihelion window that fit the comet-sun geometry and vanish in control windows after every propagation and calibration fix. It drops with a clean null. What to watch now is blind analyses from timing arrays and spacecraft, logs done by teams that would rather disprove a cool idea than nurse it. Now for the 3 measurements with the highest leverage. First, the spin and size box. Secure a repeating rotation period from multi-longitude light curves and pair it with a thermal size estimate to narrow mass. That combination either explains the missing shove through symmetry and inertia, or it makes the mismatch sharper. Second, the inbound versus outbound force box. Solve the orbit in 2 halves and ask whether the fitted non-gravitational terms change in phase and amplitude in a way that matches the measured spin. Agreement closes the book, disagreement raises the stakes. Third, the fragmentation watch. Maintain a steady cadence through the next weeks to catch any clean step in brightness, then fit any secondary with ruthless simplicity. Motion beats mood. Here is how you can follow along without specialized tools. When you hear about a new pulse in brightness, ask whether the period repeats across several nights. When someone posts a sharp image with a dot beside the coma, wait for the follow-up that shows motion night to night. When a headline screams about a flare, look for the space weather arrival that seals the timeline. When a rumor of a ping appears, ask for independent hardware and a second appearance on cue. This scorecard will change. That is not hedging. That is the job. We will move tiles up and down as the data stiffens. We will be loud about the upgrades, and just as loud about the downgrades, because pruning is how truth grows. Next, we widen the lens to bursts from deep space and ask what a smart cross-check with interstellar visitors might reveal with almost no extra cost. Deep space sometimes speaks in lightning. Fast radio bursts, FRBs for short, are millisecond flashes of radio energy that arrive from far beyond our galaxy and occasionally from its outskirts. Some are one-time events. Some repeat with maddening irregularity. A few even show rhythms that suggest a spinning or wobbling engine. They are bright, brief, and hard to catch, which makes them perfect mirrors for our problem here. What else do we miss when we only look for what we expect? The reasonable connection is not that a comet becomes a radio cannon. It is that our listening habits shape what we hear. All sky instruments sweep huge patches of heavens to catch FRBs, but they are optimized for extragalactic distances and for certain pulse shapes. They downrank or discard signals that look local, that sit near the sun, or that break template rules. Meanwhile, when an odd interstellar visitor crosses our sky, our radio attention usually stays with stars and galaxies. We do not often pivot dishes to a fast icy rock. That is a gap we can close at very low cost. Here is the modest proposal. Correlate time and sky position between FRB catalogs and the paths of interstellar objects. Do it blindly first, with no stories attached. Ask whether bursts cluster within a small, angular distance of the object during narrow windows around perihelion or close planetary passes, more often than chance would suggest. If the answer is no, we shrug and publish a clean negative. If the answer is a quiet maybe, we sharpen the test before we whisper to anyone. Sharpening means physics, not vibes. A true extragalactic FRB will arrive with a dispersion signature set by electron clouds across billions of light years. A local transient would have a very different dispersion, far smaller, and with a frequency sweep that might betray the solar wind or the ionosphere rather than deep space. Polarization angle can also tell tales. The way a burst twists as it passes through magnetic fields scales with the medium. We can use those differences as sieves that separate good coincidences from lazy ones. There is a second avenue that does not require a single lucky match. Many FRB instruments produce raw streams that contain far more events than end up in public catalogues, because aggressive filters protect against human interference. During the weeks when an interstellar visitor is at its weirdest, ask those teams to run a gentler pass on data near the comet's sky position and near the sun's limb. Then hand the longer candidate lists to a separate group whose only job is to kill them. If any candidate survives that unfriendly gauntlet, we will have earned the right to care. We can also run the experiment forward. Set a standing trigger that pings a few facilities when optical teams flag a strange visitor by simple criteria such as early activity at long distance, carbon dioxide, heavy chemistry, or a force budget that will not balance. The radio response does not need to be heroic. A handful of short pointings at several frequencies, spaced through a week, with polarization and wide bandwidth. The cost is small, the payoff is clarity. If nothing appears across several visitors, we retire the idea with gratitude and move on. If something repeats with geometry, we lean in. Skepticism keeps us safe here. The radio sky near the sun is a scrapyard of human signals, solar noise, and reflections off aircraft and satellites. Any candidate near that glare deserves to be presumed guilty until proven innocent. That is why the minimum bar for interest is 2 instruments on different continents, with different electronics seeing the same thing at the same time from the same patch, and why the next bar is a second appearance when the sky lines up again. Anything less is a story, not a result. Why do this at all if the odds are poor? Because the same pipeline that would notice a comet-timed oddity would also be better at catching solar system radio phenomena we rarely look for. Plasma instabilities in long dust tails, magnetic reconnection whistles where the solar wind carves a wake. The universe does not sort its surprises by our categories. When we widen the sieve, we sometimes catch fish we did not know to name. There is a cultural win, hidden in the technical one. A small, well-run cross-check between optical and radio teams around each interstellar visitor builds trust and habit. It teaches groups that do not often collaborate to share timing, geometry, and raw data. The first time you try it, the handoff is clumsy. The second time, it is smooth. By the third, it is muscle memory, and the cost is almost invisible. So we will look for bursts from elsewhere, not because we think 3i Atlas is a transmitter, but because listening well where we never listen is how you stop missing what does not fit the template. If the catalogs stay quiet, that quiet is information. If a pattern peeks through after every dull filter has had its bite, we will have earned a new question and maybe a new piece on the board. Either way, the experiment is worth the nights. When you step beyond Neptune, the tidy clockwork of the inner planets gives way to a wild frontier. The Kuiper Belt is a broad ring of ice and rock that holds thousands of known bodies and likely millions we have not yet logged. Most of them keep to a low tilt and gentle ellipses. Then there are the misfits. A handful of worlds loop on stretched paths, tilt at rude angles, and seem to point their closest approach in roughly the same direction. That rhyme is the spark behind the long argument about a hidden giant far away. The claim on the table is simple to say and hard to nail down. If several extreme trans-Neptunian objects share similar orientations, something massive may be shepherding them. A distant planet would tug over millions of years and leave that shared pattern behind. The counterclaim is just as sharp. Our surveys do not scan the whole sky evenly. We find more of what we look where we look. If you always sweep certain longitudes, you will keep discovering orbits that favor those views. Clustering might be a mirage born of our habits. How do we decide between an unseen shepherd and an uneven searchlight? With coverage maps and discipline. Every discovery carries a footprint that shows where and when the telescope was looking, how deep it could see, and what motion it was sensitive to on that night. When you stack those footprints across a decade, you get a heat map of attention. If the outliers cluster only where the heat is bright, bias is the likely culprit. If they cluster where attention was thin, physics is raising its hand. There are honest physical routes to weird orbits that do not require a new planet. Early in the solar system, the giant planets moved around and scattered small bodies into the deep. Passing stars during the sun's birth cluster could have tilted or stretched some paths. The galaxy itself drags gently on distant orbits and can pump their shapes over long spans. None of these explanations is as cinematic as a hidden world, but nature often prefers many small pushes to a single dramatic shove. Still, a shepherding planet remains on the board, because it would make scattered facts fall into a simpler story. A single mass far out could align arguments of perihelion, set up resonances that protect some orbits from disruption, and even explain odd tilts for a few high flyers. If such a body exists, it would likely circle the sun far beyond the Kuiper Belt on a loop so wide that even our best surveys have not yet swept it end to end. That is an invitation, not a promise. 3i Atlas touches this frontier by reminding us that our sample of outliers is young. Interstellar visitors were theory until the first one arrived, and now they are a category. The same may be true for extreme objects beyond Neptune. Each year adds a few at the edge of detection, and every new addition forces us to rerun the statistics. Patterns that look strong with 10 points can evaporate at 20. Patterns that look like noise at 20 can lock in at 50. The only cure for small number drama is more numbers. The next wave of skywatchers will help. Wide field surveys that scan the whole visible sky every clear night will erase many of the old blind spots. When the Vera Rubin Observatory begins the legacy survey of space and time, it will see faint movers again and again, filling gaps and catching slow drifters that older cadences missed. That does not guarantee a reveal, it guarantees a fairer vote. If the clustering survives under even coverage, the Shepherd case strengthens. If it fades, we retire the mirage with a nod. There is also a lesson in humility for stories like 3I Atlas. The outer system tells us that outliers are normal in a statistical sense. The tales of distributions are not mistakes. They are part of the family. Before we elevate an odd behavior to a category break, we ask whether we have simply not met enough cousins yet. That does not mean we ignore the strange. It means we measure long enough to tell the difference between rare and rule-breaking. So we keep two truths in hand. The edge of the solar system is messier than the textbook drawing, and our view of it is still incomplete. A hidden planet remains possible, but unproven. Observational bias remains powerful, but not all-powerful. As the maps fill in, either the phantom will sharpen into a world with a name, or the pattern will relax into a fair distribution once the spotlight is even. Both outcomes clean the story. Both outcomes help us weigh what counts as extraordinary when we look back toward a loud visitor skimming the inner system. Outliers are not a bug. They are where new rules get written. Physics sells us a comforting promise. The rules do not change when you are not looking. Light moves with the same speed today as yesterday. The strengths of the forces keep their numbers. Electrons dance to familiar tunes. Then you open the literature and find papers that hint at tiny wobbles in those sacred constants. Differences so small they live at the edge of our instruments, yet large enough to make theorists sit up. Are these hints real? Or are they the mirages you expect when you stare across billions of light years through a noisy universe? Begin with the fine structure, constant, the number that sets how fiercely light and matter interact. Some studies of quasar absorption lines suggest that long ago and far away, this constant might have been different by a few parts in a million. Other studies find no such shift. The honest state of play is a tug-of-war between calibration, selection, and method. If the constant truly blinks, it would change the way atoms write their spectral barcodes. If the constant holds firm, the barcodes stay locked. The only way to tell is to measure with colder blood and cleaner pipelines than ever before. Where does a loud comet enter this quiet argument? 3I Atlas gives us a laboratory to push our instruments to their finest edges in a messy, real sky. The object's carbon dioxide-heavy coma and unusual dust make it a harsh test for spectrographs that must separate faint comet lines from sunlight reflected off grains and from the infrared glow of the dust itself. If we can extract crisp, repeatable line positions from that storm, we earn confidence in the same instruments when they chase delicate shifts in distant galaxies. In that sense, the comet is not a test of constants. It is a test of us. There is a second link that is more philosophical than direct. When a model fails to close for a nearby, well-observed object, the temptation is to throw the problem upward toward new physics. Resist that urge. The ladder runs the other way. First, you exhaust the local causes: thermal lags between sunlight and venting, spin that smears thrust, geometry that turns a strong push into a quiet net, dust that scatters light in confusing ways. Only when those are dead do you give stranger ideas a minute of air. Extraordinary claims get their turn only after ordinary ones are buried. Still, a good story welcomes a stretch goal. If constants ever blink, there are clues we can collect even during a comet chase that will help future tests. We can push our wavelength calibrations by cross-checking laser comb standards against skylines in the same frames used for the comet. We can map how temperature and flex in each instrument move lines by hair widths through a long night. We can publish those drifts with brutal honesty. The habit of showing your soft spots is the habit that makes your strongest claims believable later. Pulsar timing arrays carry their own version of the constant question. They assume clocks across continents agree to exquisite precision. In part 16, we talked about how easily that agreement can fray. The discipline we practice to protect those measurements around perihelion is the same discipline that protects any search for deeper wrinkles in the fabric of time. When we subtract ionosphere noise more carefully than last year, when we track hardware swaps with better logs, when we compare independent chains of calibration rather than trust one, we are not just doing comet work. We are building a culture that can handle discoveries that would terrify sloppy teams. There is also the humility of scale. A small icy nucleus has no power to bend constants. Its gravity is a whisper. Its magnetic field is a rumor. If a timing hiccup or a spectral quirk appears this month, it almost certainly lives in our atmosphere, our instruments, or our reduction code. Naming that truth out loud is not cowardice. It is how you keep wonder from mutating into error, so do the constants blink? The fairest answer today is probably not in any way we can prove with this visitor, but the chase gives us a chance to sharpen the very tools that would reveal a real blink elsewhere. Think of 3i Atlas as a stress test that turns fancy instruments into reliable ones and turns bold teams into disciplined ones. If the constants hold, our improved methods will say so with more authority. If a future sky whispers a change, the same methods will be strong enough to hear it. The thread through this chapter is maturity. We can be thrilled by the idea that the universe keeps secrets while insisting that our first duty is to remove every human-made ghost. We can admit how much we want a surprise while proving that our wants are not steering the data. If the numbers stay loyal to old rules, that is not a defeat. It is a win we can bank. If they ever stray, we will know it because we were careful when it was unfashionable to be careful. That is how you earn the right to rewrite a page in the book of nature. Every night, the sky writes a book our eyes cannot finish. Telescopes pour out images, spectra, timing logs, and radio streams faster than any team can read. That is where machines help. Not to replace judgment, but to widen the net and catch the odd threads we would otherwise toss as noise. 3i Atlas is a perfect stress test for this new habit, because the signals we care about are small, fast, and easy to miss when we rely on human reflex. Start with a simple truth. Classic pipelines are built to find what we already expect. Smooth brightening curves, familiar spectral lines, trajectories that match tidy functions. They protect us from false alarms by shaving off anything that looks messy. The risk is obvious. If reality hides in the mess, the filter becomes a blindfold. Machine learning lets us flip the stance. Instead of asking, does this match a template? We ask what does not belong. The result is a short list of outliers we can examine with human care. Here is a concrete play that fits this visitor. Feed high-cadence light curves from multiple sites into a model that only learns the repeating heartbeat of rotation and the slow drift from heating. Ask it to flag intervals where the rhythm changes in ways that are unlikely across all sites at once. That is how you catch small fractures the moment they begin, rather than a day later when the coma has already smeared the clue. Pair that with the second model that watches polarization versus phase angle and highlights curves that refuse to slide back into the family band when geometry changes. The goal is not a verdict. The goal is faster triage. Spectra get the same upgrade. Train on many comets to learn the usual dance between water, carbon dioxide, and dust glow as a function of distance. Then let the model point to frames where the ratio misbehaves in a way that cannot be explained by temperature or aperture effects. That is how you spot layering or fresh vents as they wake, not after they have rewritten the coma for a week. Every hour you save turns into cleaner physics when you solve for the missing shove. Astrometry and force models benefit too. A lightweight learner can watch residuals from nightly orbit fits and ring a bell the moment the inbound solution and the outbound solution begin to part in phase with a measured spin period. Humans can do this by hand, but machines do it while we sleep and without bias toward the pretty answers. When the bell rings, we move telescopes. When it stays quiet, we save nights for other targets. Attention becomes a scalpel instead of a floodlight. Radio and timing pipelines are where discipline matters most. Let a model cast a wide net near the sun's glare and keep candidates alive that old rules would kill. Then hand that noisy basket to a second, meaner model, trained only on interference and instrument quirks. Anything that survives both sides earns human time and a second attempt under the same sky geometry. The two-step saves pride. It also saves hours that would otherwise drown in false hope. There are hard limits, and we should say them out loud. Machines love patterns, even when patterns are accidents. They can be confident and wrong in a way that flatters our wishes. The cure is replication and pre-registered tests. Before the model runs, We write down what will count as a real alert. 2 longitudes for light curve anomalies, independent instruments for narrow radio features, a fixed gain change that must be seen when the rotation phase repeats. If an alert meets the list, it moves forward. If it does not, the model learns, and we do not move a single telescope on a rumor. Open practice turns clever code into community power. Release weights, training sets, and failure cases. Publish the nights when the model cried wolf and the nights when it saved a clue. Invite a rival team to run the same code on their raw frames and list where the answers disagree. The friction is the feature. It forces both sides to tighten calibration and to explain assumptions that were invisible when the code lived on one machine. You can feel the culture shift in small logistics. A comet trigger that posts rotation phase predictions every morning. A shared dashboard that shows inbound versus outbound force fits in near real time. A standing slot at a radio array that can be flipped on by a simple threshold rather than a phone call. None of this is glamorous. All of it turns attention into precision. If 3i Atlas settles, the machinery still matters. The next visitor will arrive with its own quirks, and our upgraded sieve will be ready. If it refuses to settle and the numbers keep tapping on the glass, we will have the tools to hear the taps faster, kill bad leads sooner, and pour time into the few threads that stay strange under every light. That is how machines earn a place in the room, not by shouting, by noticing, then letting us decide what the noticing means. When the cameras power down and the plots stop updating every hour, the story does not end. It spreads out and sinks in. Numbers that once felt like live wires become quiet lines in a ledger. Hypotheses that sounded bold during the rush turn into sentences you can defend in a room full of people who were not there for the noise. That is the real arc of a sky mystery. It begins with a flare and ends with a page you could hand to a stranger 20 years from now, without apology. 3i Atlas gave us both the thrill and the patience drill. It woke at an unfriendly distance. It breathed carbon dioxide like a cold world that never learned the inner system's rules. It scattered light in ways that made the polarization charts blink. It forced us to count jet thrust like accountants. It walked a near-plane path that made every close approach feel like a setup even when the math said coincidence. It asked for every boring check we could muster, and then some. That is a gift, not a burden. The best teachers are the ones who make you earn easy words. If the trail now bends toward ordinary, we thank it for making us better. Better at reading light curves for spin without fooling ourselves. Better at pairing spectra with polarization so dust descriptions are not poetry. Better at splitting inbound and outbound force fits and letting a measured rotation period tell us which way to lean. Better at running small cross-checks between optical teams, radio dishes, and timing arrays without turning coordination into theatre. Ordinary is not an insult. Ordinary, after you tried to break the model and failed, is a win with interest. If the trail refuses to settle, we will not be surprised in the way that makes people shout. We set the bars early. Unpredictability that outpaces tweaks. Impact that moves doctrine, not just press. Irreversible fingerprints that force future work to bend. Signals or behaviors that survive dull corrections. Any step over those lines will be obvious, because we have lived beside the lines for weeks. The worst way to meet a revelation is to be unprepared for your own standards. The best way is to have written them in ink before the twist. Either way, the next visitor is already inbound from someone else's sky. The pace is going to quicken as surveys learn to spot faint things fast. That means our muscle memory matters more than our metaphors. When the alert lands, we will not argue about whether to watch. We will decide what to watch first. High cadence photometry across longitudes to lock rotation. Polarization at changing phase angles to tag dust. Spectra that track the carbon dioxide balance as distance changes. Orbit fits that respect mess rather than pretending to be smooth. Radio time on a quiet piggyback when the optical flags say this one is odd. A short list, run well, wins more truth than a long menu that never cooks. There is also the quiet work of making the public part of the craft. Curiosity brought a crowd to this story. Honesty keeps them. That means showing how a claim gets stronger or weaker with each new measurement. It means saying we thought X because of data Y, and we now think Z because we fixed a calibration and the plot moved. It means praising a clean null result as loudly as a spike. It means reminding people that discipline is not the enemy of wonder. It is how wonder grows up. Risk lives in this work, and we should name its shape. Not the risk of asteroids in this season, but the risk of habits that can harm future choices. If attention trains us to chase every outlier with sirens, we will waste our best instruments and teach the public to distrust the next quiet month. If caution trains us to shrug at every outlier, we will miss the moment the tale of the distribution whispers a new rule. The cure is not a mood, it is a checklist. We can love the sky and still make it earn every headline. There is a final, softer truth I want to leave with you. The universe is not obligated to be theatrical. It is obligated to be real. Sometimes real looks like a spectacular break that seeds a new class of objects and gives school kids a new chapter to memorize. Sometimes real looks like a loud comet that turns into a patient lesson in how ice and rock behave when sunlight pushes and dust flows. Both are worthy, both move the frontier, both are worth staying up for. So we put away the late-night coffee, archive the raw frames, and write the last lines of this chapter with the same care we gave the first. 3i Atlas may leave as a once noisy guest who taught us to count better. It may leave as the first hint of a rule we did not know to write. Either way, the plan is the same. We keep our instruments honest, our models humble, our teams coordinated, and our language clear. We let attention buy patience instead of panic. We welcome the next dot on the sky with less noise and more skill. Somewhere out past Jupiter, a small body is cooling, dimming, and turning its face toward the dark. Somewhere inside a server room, a process is chewing through last night's data, learning to notice what we were trained to ignore. Somewhere on a hill, a telescope operator checks the wind and smiles because the schedule says the same strange visitor returns in the morning for one more look. The night is long, the work is longer, the wonder is longer still.